Okay, so last class, we talked about how we can assume all inputs are just binary strings. We don't have to do this composition, decoding, and everything every time. We just do it once, and from now on, we are safe. And it gave us a very concrete way to formalize the notion of, okay, what would it mean to solve a problem, right? So you have some function which is well defined on some inputs, and you want to capture its input-output behavior in your computational model. And the function space was simplified. It's just taking binary string as input and giving a binary string as output, okay? And then we defined our first circuit model, our first computational model, Boolean circuits. And what we are going to do today is basically study properties of this model. Okay, so we will see what it means to compute in this model. There's this important notion of equivalence between models that will again, it's a fundamental notion in computer science. You see it we'll again see it several times throughout, but this will be our first instantiation of it. And then we will study what's the power of this model, okay? That's our target for today. But before going on, let me make a couple of announcements. Okay, so first is that homework 1 will be out today at 6 p.m. on Gradescope. Okay, so there's, yeah? So the Gradescope for the class has been created. It is live. I'm able to see it. But if you're not able to see it, there's also, you can sign up for it using a direct code. But you should see it on BruinLearn because it's linked through BruinLearn. And I also see a few students are already registered on it. But make sure you only register once using one email account, okay? That's about it. And you should be able to download the PDF also via Gradescope, okay? And the deadline for submission is a week from now, which is 10/13 at 10 p.m. Okay. And as I said, the homework is graded for effort, but make sure you attend the problems. That will go a long way towards helping you on the exam. Okay. Any questions about the homework? All right. And if trouble if you have trouble, reach out to a TA or use the code. If the code is on EdSTEM, you can see it and then register using that. Okay. All right. Now, so in last lecture, we ended with the definition of Boolean circuits, right? So we defined Boolean circuits. I'm not going to write down the entire definition, but there are three important things. C is a NMS Boolean circuit. Right? So meaning it has n inputs, number of outputs, and the size. Okay? All right. So in the way we define Boolean circuit, there are two ingredients, right? One, we had the DAG, the directed acyclic graph, which tells you how to put together the simple pieces, what order you would compute them and so on. what order you would propagate the values from inputs to the output. And the other thing is this set of simple operations that we were allowed, right? I said you can think of Boolean circuits as you're given, bags of Lego pieces, three kinds. One you have AND pieces, one you have NOT pieces, and one you have OR pieces. And you're using these Lego pieces to put together, a new circuit, and then see what you can do with that new circuit. Okay. One immediate question, besides AND or not being natural, is, why should we only consider those simple operations? Okay. And one reason is that these have been studied as logical operations for a long time, even before people started thinking about computing. And the other thing is that you can recover or implement these things in practice. Right? We saw a fun demonstration using fluids. I mean, there are more things. There's something called shooting tumble, where you can use marbles to simulate these things. And this is literally Digicomp 2 is a place where you can use these gates to somehow model these knobs to configure what gate they're computing and then wire them some way and then do some computation. And the way you do it is you drop some marbles depending on what your input is, and then voila, you get some output, which is exactly what you want it to be. Okay? There are lots of fun things like this, if you want to. I mean, fun as in fun in some space at least. Okay? But it's not necessary for us to only look at these simple operations. Okay? Right. There are many other options. So let's look at a couple and see what they lead to. And one important class is NAND operations. I mean, it's important for pedagogical reasons, because it will help us simplify some things. And NAND is a very simple operation. And it's defined, it's in the name, it's not of AND. Okay, that's why it's NAND. So NAND is a basic operation which takes 2 bits as input. And is just not of AND of A comma B. Okay. Just as we define XOR 2, XOR 3, and so on, here is a different function, NAND. And we can take that also as a simple operation. Okay. And it is important enough that it gets its own symbol. Which looks almost exactly like the AND, except for the circle at the end, which signifies you have a not operation at the end. Okay, it's not of AND. All right. Okay. So now we can define a very similar model as Boolean circuits. Okay, I can say I'm not going to write all of the nitty-gritty details, but I'll tell you the main principle. So I can define a NAND circuit just as before, right? So a NAND circuit is going to be a DAG where you have n inputs, x0, x1, all the way up to xn minus 1, just as we did before. We have S gates, but this time all are labeled NAND. Okay, you're not allowed any other simple operation or gate, just NAND gates and nothing else. And then you also have M nodes in the graph which are assigned y0, y1. Okay, yeah. Only NAND gates. Okay. You can define a combination if you want. You can define your favorite other circuit, but right now NAND gate just means only NAND gates are allowed. Nothing else is allowed. Okay. And one thing which is, maybe I was not explicit enough about this even in the last lecture is you're always allowed to hard code input values. Meaning, for example, if I want a wire to always have the value 0, I can just say I set that input to be 0. Okay? Meaning you are allowed to have constant zeros and ones if you want. All right. And just as before, I can define a function now, a NMS NAND circuit defines a function which takes n inputs and outputs m outputs. Okay, just exactly as we did for Boolean circuits. You would follow the exact same thing. You start with the DAG, you find a topological ordering, you layer the vertices. So the input variables are in layer 0, and then you propagate values from left to right. Okay? So we follow the same exact notion, same exact definition, and you would get in a function which takes inputs and converts its output depending on what circuit you pick. Okay? And lastly, just as we did for Boolean circuits, we can say a NAND circuit C computes a function f if okay, so I have a function which takes n inputs and m outputs. Okay, we'll say an AND circuit C computes a function if the same exact thing that we had for Boolean circuits holds, which is for every input, the output behavior is exactly what you would want under the function f. Okay, this is just to give an example, right? I can also define in the same way. We can also define XOR 2 circuits if I want. Okay, I can also define XOR 3 circuits if I want. If I want majority 3 circuits, those also I can define, and so on and so forth. Okay, we'll talk about many of these things later on, but briefly, but we'll focus only on Boolean circuits and AND circuits for the most part. Okay. All right. So now we have our first sort of meaningful relation between computational models. You can think of two different computational models. One is Boolean circuits, where the Lego pieces that I give you are just ANDs, ORs, and NOTs. And you can imagine, there's another, room where I give you a million AND pieces, but no AND or NOT pieces. Okay. Now the question is, what can you do with each of these different sets of basic operations? Okay. And fortunately for us, there are some very clean relations between these computational models. Okay. And this is one of the more important questions we study in theory of computing, which is suppose you define two different models. Okay. You can ask, okay, what can each one compute absolutely on its own? And you can also ask, okay, how are they related to each other? Is one more powerful than the other? Okay, you can ask a relative question. You can also ask absolute questions. We'll ask both of them in a second. The relative question is the first one that we're going to address. Okay. So we'll say a function f is computable by a Boolean circuit if and only if it is computable by an AND circuit. Okay. We're saying for a function f, suppose there is a Boolean circuit computing it. Then there is also an AND circuit computing it, and vice versa. If there is an AND circuit computing it, there's also a Boolean circuit computing. Okay, this is showing that there's an equivalence between these two models. Whatever you can do with one set of pieces, you can also do with the other set of pieces. Okay. Any questions about the statement? Like, just the meaning of the statement. As I said, this is a first example of equivalence between models. We'll see many other similar sounding theorems later on. Like we'll say, okay, model A is equivalent to model B in the sense that whatever you can do under model A, you can also do in model B and vice versa. Okay. All right. So suppose I want to prove this thing. How would I do it? As I said, proof is really, you're really designing an algorithm, right? So you have these two bunch of Lego pieces. You want to say whatever I can do with one, I can also do with the other. How would you do it? Yeah?
Couldn't we just show that like every element in a Boolean circuit can be constructed with NAND gates?
Exactly, right? If I can show that the basic pieces can be built, then I can replicate whatever you were doing with the first set of pieces. Okay? So it all comes down to whether or not, because we are not very worried about the size for now. We're just saying, is it computable or not? Okay. And the translations for size are also, these are all very efficient conversions, so you don't have to worry about that. But we're not asking even that question. We're just asking, whatever I can do with the first model, can I do with the other? Okay. And so let's see, right? So first, this direction is easy. Suppose, okay. So if a function is computable by a NAND circuit, then it is computable by a Boolean circuit. Okay, so this is kind of the easier direction to prove. And what do we need to prove it? We need to show that if I give you a NAND operation, how can I simulate it with just Boolean operations? Yeah, exactly. Right, so it kind of, we are given these pieces. So every NAND, I can just go to my NAND circuit and replace it with an AND followed by a NOT. Okay. So in some sense, actually, I can simulate every NAND circuit even with just AND and NOT gates. I don't even need OR gate, but OR can help sometimes in reducing the size, as we'll see. Okay. So I might technically double the number of gates involved, right? Every NAND gate is being replaced with two gates, one AND and one NOT. Okay. But that's okay. We're not worried about the size for now. We're just trying to find out, does there exist a circuit to do this or not? Okay. All right, so now to do the other direction. Okay, so you want to show that if a function is computable by a Boolean circuit, then it is computable by a NAND circuit. Okay, so one thing to note here is that unlike what we're doing now, sometimes proving equivalence between models is way more complicated. Okay, here at least it's simpler because it's kind of baked into the definition of the model, right? The definition says you're putting the simple pieces together, right? If we can just show how to simulate the simple pieces, the rest will follow. Okay. For some other models we'll see later on, it's not so immediate, and you have to, such equivalences can be much more involved and sometimes very surprising. Okay. All right. So to do this, we had to walk through each of the simple operations and show how you can simulate them with only NAND pieces. Okay. So let's take the first piece. Maybe this is the, well, let's just start with not. So I want to replace this not pieces by something which only uses NAND. How can I do that? Any guesses? So what should not do, right? If I send a 0, 1 should come out. If I send a 1, 0 should come out. So how to mimic this behavior with only NAND gates? Yeah?
Well, that's it. So it's whatever you want to take them out of.
Okay, so I think this is what you meant, right? So basically, my input is something. And I'm going to split it. So A, and this is NAND. Okay. My claim is that NAND of A comma A is really just not of A. Okay. We can check that. If I put in a 0 here, what do I get? I get NAND of 0 comma 0, which is 1. Right? And if I put in a 1, I just get NAND of 1 comma 1, which is not of AND of 1 comma 1, so which is 0. Okay, so we match the behavior. So now every NOT gate that you see, I can replace it with a single NAND gate with this kind of duplication. Okay, and remember, we were never charged for wires, so that's okay. Okay, you can ask more fine-grained questions where you also limit the number of wires and so on. But right now, we're only asking the first question, which is, okay, what can I compute with these models? Okay. This is for NOT. Now, how about, let's say, let's do AND. Okay, how can I simulate the behavior of AND with only NAND questions? 1 second. So, yeah. Not the NAND, right? So is that what you had in mind? Exactly, right? So, we are, I'm going to say this joke many times, we are computer scientists. We always reuse the work that we already did, right? So we already saw how to do NOT. So NAND is basically, we're doing a double negation. So AND is not of NAND. Okay, so what can I do because of this? Move this down here. So I can say, my simulation is just AB, go through an AND, and then do another NAND. Okay, so we just replicated the NOT gate from above. Okay, so every AND gate gets replaced with 2 NAND gates, and we have a circuit. Okay, the last thing we need to do is the OR. Okay, so how can I replace or mimic the behavior of OR with only NAND gates? Any suggestions? Yeah.
We have an AND and a NOT, so we know by like the Morgan's law, we can just like, I think, yeah, we can just emulate it. I forget exactly.
Well, it's small enough that we can, I guess what it is. But let's see if, yeah. Okay. This is correct. Okay. So OR of A comma B is basically saying that you don't have both being 0. Right? So when both are 0, not of those things will become 1, and then NAND will be 0. Okay, so you can check that this identity holds by giving in explicit, like, just check 0, 0, I get 0, anything else I get 1. Okay. And once we have this formula, we can, of course, just do what we were doing, right? So this is A. I have to do the negation, but we know how to do not already. I should put that circle, that's important. Okay, so every OR gate gets replaced with 3 NAND gates, and then you have the same functionality. So I can mimic the behavior of Boolean operations with only NAND operations. Okay, and this leads us to one very simple to state, but I think very nice and clean conceptual statement that Boolean circuits are equivalent in computational power to NAND circuits. Okay, so meaning equivalent in computational power, meaning if something can be realized by Boolean circuits, then it can be realized by NAND circuits and vice versa. All right. Okay, so we also talked about other gates, right? As I said, we define NAND circuits, we define Boolean circuits. I can define XOR 2 circuits, I can define XOR 3 circuits, majority circuits, and so on and so forth. Okay. And just based on what we already did, suppose I consider a model of XOR 2 circuits. Okay, so I'm not even going to write down the formal definition, but you know exactly what I mean, right? So you replace the basic operation from being NAND or AND or 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 not with just the XOR 2 operation that we defined a couple of lectures ago. Okay, and just to remember, XOR 2 of A comma B equals 1 if A plus B is 1. Okay, if exactly one of those bits is 1, you output 1, otherwise you output 0. Okay, and I can define a circuit based on that. Take a DAC, connect the wires, and then you progress from left to right, and you get an answer. Okay, and we saw how to compute XOR using Boolean circuits, right? So this was basically equal to OR of OR of right? So, and we built a circuit for it a couple of lectures ago. So one implication of this is that if F is computable by XOR 2 circuit, then it is computable by Boolean circuits. And hence also by NAND circuits. If someone gave you XOR 2 pieces, I can mimic that behavior using just the Boolean operations or just NAND operations. Okay. Now, on the other hand, let's say I give you a million XOR 2 pieces, these million XOR 2 gates. You still cannot simulate a single AND using that. Okay, that's something that we're not going to prove, but it shows that there's something. While there are many choices for what simple operation you can pick, you have to be a little bit careful. For instance, so even if I give you again, million is just a big number. Pick whatever number you want. We cannot simulate and. We cannot simulate and of two things. Not is very easy to do using XOR. Like if I hardware one bit to be 1, you immediately get not, but you cannot do and. Okay? It's not something we're going to prove, but it's something that is true. Right? So in some sense, you can't just pick any set of simple operations that you want. You have to be a little bit careful. Right? And in the homework, you'll prove another such limitation, basically saying in Boolean circuits, we have and, or, and not. Right? If I drop not, you end up with the same problem again. I can give you a million and or pieces. You cannot compute, for example, the not operation using them. Okay, so you need not along with the and or. All right. So this means that at least some models are less powerful, right? Because every XOR 2 circuit can be simulated, can be computed by a Boolean circuit, but not vice versa. That's what one direction is relatively easy. In fact, that's what we showed a couple of lectures ago when we wrote down the circuit for XOR 2. But the other direction, I'm stating with that proof, is also true. Okay, so XOR 2 circuits are strictly less powerful than and or circuits, than Boolean circuits. Okay. All right. That kind of suggests that maybe Boolean circuits are very good, and in fact they are very good, and so are NAND circuits and so on. And the reason they are very good is because the following. Okay, we want to rule out the possibility of something similar being true for Boolean circuits. Maybe what if there is some other function that I cannot compute with Boolean circuits? Is that possible or not? If it is, then we are in trouble with starting with these as our basic operations, right? So we want our basic operations to be simple enough, but also powerful enough that if I form a long enough sequence, I can do any computation that I want. Okay. So our first sort of, maybe let's say major theorem is going to be the following. So we're going to show that every function can be computed by a Boolean circuit. Of size something. I'm going to write down the size in a second. But the most important thing is that every function can be computed by Boolean circuit. So Boolean circuits are very powerful as you can expect. Any function, I can write down an equivalent Boolean circuit. It's n times m times 2 to the n. Okay. So the size is big. There's no hiding that. Okay. But remember, this is an upper bound. Right, so we're just saying that every function has such a circuit. But of course, for some functions, I might do much better. Okay, so for example, so you shouldn't take this n times m times 2 to the n as like always the best possible. It's just saying that I can always do it with these many pieces. Okay, but for some functions, I might even be able to do something better. Okay. So for instance, if I define add, which is takes 2 Boolean strings and gives out another Boolean string where addition is defined as basically in binary notation. Okay, this is some function. Then it is a non-trivial result, but you need to spend a little bit of time to figure this out. But there actually exists a Boolean circuit for computing the addition operation, which is super efficient, just a constant times n many gates. Okay. So if I want to add n bits, n bit numbers, then I just need something like 4 times n many gates or something like that. Okay. The general bound is exponentially larger. It's like n times 2 to the n, which is a huge number. But for some functions, you might be able to do much, much better. And then, for example, for multiplication, you can show that mult can be computed. So even if you use grade school arithmetic, you can do it in O of n squared gates. Okay. You can also do it in, even the more sophisticated multiplication algorithms. You can also design specific circuits with very few gates for them. And these specific circuits are heavily engineered now. Like, if you have some specialized hardware, what they do in some sense is for some specific values, like let's say n is 16, I'm going to build a circuit which only has these gates and computes this multiplication using as few gates and time as possible. Okay, so figuring out the best possible circuit for a given function is a very important primitive that's been optimized for the basic operations to no end. Okay, and if you think about something more sophisticated like programmable GPUs, FPGAs, and so on, you're kind of playing the same game, which is I have some basic operations which are now a little bit more sophisticated. Maybe my basic operations are small matrix multiplications. My basic operations are small multiplication operations, and so on. But how do I mimic something bigger on using as few gates or as few of the small operations as possible? Okay, you might change your set of base operations, but the principle is not changing, which is I have some slightly more complicated thing. I want to break it down into as few of the small operations as possible. Okay, so that's for kind of the next level information that you would like to extract. How many gates do I need? But even the general statement should be very surprising, because it's saying every function I can compute with just Boolean circuits. Okay. Any questions about the statement of the theorem? But as I said, definitions are the most important. Second most important are the theorem statements. You need to understand what they mean, and then we'll talk about the proofs in a second. All right. So let's talk about the proof. And okay, so I'm going to prove kind of the 1-bit version. The general version is basically the same. Meaning, suppose I have a function which only outputs 1 bit. Okay. All right, so the only difference between these two is that I'm setting m equals 1, And I'm going to prove this special case where m equals 1, where there's only one output variable, and the general case is exactly the same. You just do it m times and you get the bound. Okay? But this already captures all of the main ideas, so let's just focus on this case of 1 bit. All right. Okay. And the way we'll prove it is basically by kind of building a circuit in a brute force manner, right? So what do I mean by that? So what do we want to say, right? We want to say that give me any function which takes n inputs and outputs a single bit. There is a Boolean circuit which captures this function. Okay. So let's picture what this function would look like, right? As I said, we can think of functions as truth tables. Right? So we have input and then output. For example, maybe when the all zero string is the input, the output is a 0. Maybe if I have a 1 at the very end, the output is a 1, and so on and so forth. Okay? Maybe if everything is a 1, I have a 0 again. Right? So I have every possible input here. And how many inputs do I have? I have 2 to the n inputs corresponding to all possible n-bit binary strings. And for every possible input, I have a specific output that I have to realize. Okay? And we will build this circuit by, again, by doing something which is kind of like a reduction. Okay? We first identify some special functions that we can compute by Boolean circuits relatively easily. And then we'll see that, okay, I can use this to build any other function. Okay? So what are these special functions? These are basically just checking for equality. Okay? So for any string, I'm going to define a function E alpha, which is just going to check if your input is equal to alpha or not. Okay? Where E alpha of x is 1 if x equals alpha and is 0 otherwise. So for instance, let's say n equals 2 and we take alpha equals 1 comma 1. What does this function correspond to really? What is this function? We've seen it before. So what is it saying, right? I have to output, yeah? I mean, in this case, it's actually just the AND function, right? Because I'm checking equality with 1 comma 1. So so let's say I do x1 comma x2, then it should be 1 if x1 equals 1, x2 equals 1, and 0 otherwise. Yeah, which is just the AND function. Okay. And similarly, if n equals 3 and I said alpha equals 1 comma 1 comma 1, then I get is just again AND really. Oh, I should remember, let me use 0 indexing. Okay. you can generalize this. You can also wonder, okay, so what if n equals 2 and alpha equals 0, 0? Right, so then I'm saying, I have to check if it's actually equal to 0, comma 0, right? You can check that it's basically or not of or. But the special examples are just to give some intuition, but at the end of the day, this is a very simple function. Over the entire input space, it's going to take the value 1 at a single point and nowhere else, right? So if I were to write down the truth table for E alpha, what would it look like? Okay, there would be some row corresponding to alpha where the output would be 1 and every other thing would be 0. Okay, this is what the function looks like. Very, very seemingly silly, simple function. Okay? Any questions about the definition? All right. So let's walk through this slowly. Maybe one way to think about how we're going to prove this theorem is to study some case exam, some kind of case analysis. I'm going to come up with a series of functions and we'll check, okay, can I compute this function using Boolean circuits? Can I compute this function using Boolean circuits? And at some point we'll realize that basically what we've computed is enough to capture everything. All right? So as perhaps a example of a general theorem, trying to understand the power of Boolean circuits, let's say even alpha is all ones. I want to say that the function E alpha, where alpha is all ones, is computable by Boolean circuits. We really want to show this for every function, but let's start with this simple function. We'll see why it's useful in a bit, but let's ask, okay, what happens if for equality with all ones? Can I compute that with the Boolean circuit? Any suggestions for how I might be able to compute this? Yeah? It's just the and, right? So basically, what are we checking? So E1111 of x is 1 if and only if x0 equals 1, x1 equals 1, and all of the input bits equal 1. Okay? It's an AND operation of n bits. But technically speaking, our AND gates only involve 2 bits. Right? We are allowed the simple Lego pieces which only take 2 wires at a time. Okay? But here I have to do the AND of n things. So how can I do that? Yeah? Exactly, right? So you're basically going to chain these things. Right? In fact, this is how circuits are built. When you want to compute something bigger, you just chain things. Okay? So that's exactly what we're going to do. So here's my circuit for it. All right. Let me be colorful. Okay. So let's say this is x0, x1 up to xn minus 1. So this is the AND operation. I chain it through another AND. chain it through the next AND, and so on. Okay, and the final AND will have my answer. Okay. All right, simple enough. And how many gates did we use here? We basically use n minus 1 gates, right? So 1 and 2 and 3 and all the way up to n minus 1 gates. Okay, so quite efficient if you think about, and then everything is going through 1 and, so the number of gates is n minus 1. Okay. All right. That's for one special function. What did we gain from that? Well, it's a case analysis. As I said, we'll build these things one at a time, and then at some point we'll realize, we've done actually most of the work. Okay. So let me take another example to try. And this example is the equality function again, but this time, let's say the first bit is a 0 and everything else is a 1. Okay, my claim is that I can also compute E of this alpha as a Boolean circuit. Any suggestions on how? Yeah? Right, exactly, right? So the suggestion is, it's again, we are checking the quality of every bit, right? So the first bit should equal 0, the second bit should equal 1, and so on, right? So in some sense, the only thing that I really need to change is I can send this x0 through a NOT. Okay. Now hopefully you see a pattern. How about computing E alpha for any alpha? In sessions, now, I might not have a 0 at the first bit. I might have 0 in position number 11, maybe 0 in number position number 17, 35, 75, whatever you want, right? So arbitrary string alpha. How can I compute E alpha for those strings using kind of a Boolean circuit? Any sessions? Yeah? Exactly, right? So it's kind of the same principle. We already did it for all ones. We also kind of saw a case where one bit is 0. If I tell you the third bit is 0, what should you do? I should put a NOT here, and that's it. Okay? I basically same template, and depending on whether the corresponding alpha bit is 0 or 1, I'll decide whether or not to put a NOT gate. Okay? So for general alpha, I would just say follow the same template, but every time put a NOT gate if okay. I might put a NOT gate on every wire. For example, if alpha is all zeros, then I have to put a NOT gate everywhere. Otherwise, nothing else is changing. Yeah. Yeah, so we can do an accounting, right? So right now, we are just trying to say that there is a Boolean circuit, but we can do an accounting now, right? So what did we end up with? For every E alpha can be computed with a Boolean circuit, right? And the size of the circuit, the number of gates that we use is, I need to have n minus 1 ANDs, okay? But I might have some number of NOT gates as well, okay? And I'll have at most n NOT gates. I might, basically negate every variable. So the total number of gates that I would use is at most 2n minus 1. Okay, that's an upper bound. Upper bounds are fine for us. Okay. So just to give like a, maybe a very concrete example, let's say alpha is, maybe 1, 0, 1, 0, then so what do I have? So this wire goes as it is. The second wire gets a NOT, go into, and remember there's one more AND here, and one more AND here. Okay, and this wire goes as it is. This wire gets a NOT as well. Okay. And the number of gates used is 3 plus 2, 5. Right? So what did we learn from this? We saw that, okay, some simple functions, these equality functions, at least we can compute those using Boolean circuits. All right? And as we'll see when we, we'll take a short break, but when we come back, we'll see that basically we've done most of the hard work. Given these pieces, we can actually compute any other function relatively, at least easily from now. Okay? You have a question or?
Saying like this input, like output path to that.
Yeah.
It's like putting the equalities like.
Exactly. That's what we're going to do. Okay. So, we've done most of the hard work more or less. When we come back, we'll put these things together to compute any function. Okay. Let's take a short 5-minute break.